Okay, now that we've introduced this notion of an impedance matrix versus an admittance matrix, the next question is, how do I determine, via measurement or calculation, these individual elements of that matrix? So remember, in your head, we have these equations here. V is z times I, or yv is equal to I. So these are matrix vector equations, but buried within them is all of these terms in this matrix. So I want to know how to quantify these parameters inside this matrix. What do they represent? And how would I maybe measure them in the real world? So let's write out, say, the first line, or the ith line, I'll say. So v sub I is equal to z sub I1 times I1 plus z sub I2. So remember, this I represents my row going down. So I could be, say, the second row would be a 2 for I, or the third would be the third row. So now I'm at the ith row. So this is I2 plus dot 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 plus z sub I n. So it's an n port network times I sub n, right? So this is from the definition of this matrix vector notation, right? So if I were to say V22, you do the column row scan like this. So it would be 2, 1 times I1 plus 2, 2 times I2 plus 2, 3 times I3. Or if I go down to the ith, you do that same thing. I1 times I1 plus z sub I2 times I2. So don't confuse the little I with the big I. And then z sub In times In. So it's that same sort of row column scan happening on a particular row. So what you do then is, I may be given a particular circuit, right? I could hand you a circuit diagram with a bunch of inputs and outputs for all these ports. And I'm going to say, calculate the impedance matrix for this circuit. So what you can do is, basically, you have the freedom to kind of play with these terms. Okay, for example, suppose I set all of my ports to an open circuit. Well, that means no current will be allowed to flow into or out of any of these ports. Or I could hypothetically short them all, and there would be no voltage at any of those ports either. Okay, so I would have the circuit itself, but I can do things to those ports to try and influence these other parameters accordingly. So this should kind of be familiar in the sense that we're doing essentially like the n-port equivalent of a Thevenin equivalent circuit, right? And we'll do an example to sort of clarify what's happening here. But just, as a basic example, keep in your mind something as simple as a T-junction. Sorry, so there's 3 ports here, and I could hypothetically excite this one here with some voltage and leave these as open currents, or I could short this guy here, or I could force a current to go into here and measure what the voltages are at the other terminals. And that would tell me all the information I need to know about what's going on between all of the ports. So what you would do is, step 1, set all ports to open circuits, except for the jth, so the one I'm interested in. So this would maybe be the jth port here, and this might be the ith port over there. And then when I set all of my the open circuits here, I can then measure, or I can excite that jth port, with a current. So excite port J with a current source, I sub j. And again, we will do examples of this, so don't feel bad if it doesn't quite make sense. But this is a sort of generalization of the Thevenin equivalent circuit notion here. So we set all of our ports to open circuits, and then I'm going to excite J here with some current source, and then I will just measure the voltage at port I. So, okay, step 3. I'll say measure voltage V sub I, like that. And then, by definition, Z sub ij will be equivalent to the voltage I measure at port I divided by the current injected into port J under the condition that I equals, I'll say I sub n equals 0 for all n except J is the idea. So what I'm saying is you set all of your ports to open circuits except for one, which I'm going to excite with some current. And then I'm going to measure the voltage. And by setting all these to open circuits, I am not allowing any current to flow through them except for the one that I have excited. So that's kind of how the book describes it here. So you would basically say where I1 equals I2 equals I3 equals ... equals IN equals 0 except ij, the one I've excited. Okay, so that is how I would measure this impedance element in my matrix if I had a real device. Okay, so you can imagine I could do this in like simulation or theory if I gave you a complicated circuit, or hypothetically, I could give you a real device, just a black box with a bunch of inputs and outputs, and I want to know what is the cross impedance, I guess, between all of those little ports, and this is how you would do that procedure. You would leave them you would excite one of them with a known current and leave all the others as open circuits and see what voltages develop. Equivalently, you could also do a similar procedure, only you would do Y sub I. I can do the impedance matrix would be defined as I sub I over V sub J, where you would say V1 equals V2 equals V3. So I would put short circuits on all of these ports to enforce them as 0. ... My nth are 0, except V sub J. Okay, so the idea is I would excite one of these ports with a voltage and some currents would come flowing out of the others because they are short-circuited. All right, so that would allow me to determine the admittance matrix. And then, of course, Y is equal to the inverse of Z, and vice versa, Y inverse is equal to Z. Okay, so that is how you would measure measure or calculate the admittance matrix, this big monster here, for any sort of n-port microwave network. That's the procedure there. And you can see how it kind of falls out of this definition, which we've written up here for a single row, right? Because if I open the circuit at a bunch of ports, I am forcing this guy to be 0 and say that guy to be 0, but not him. So all these other terms are zeros, which means V sub I would be equal to Z sub I2 over I2, or excuse me, right? If I set this to 0 and I set that to 0 by opening the ports, and I only leave one of these terms left, then we'll write this over here. You would have V sub I is equal to Z sub I2 times I2, which would then imply ZI2 is equal to V sub I over I2. Only instead of a 2 here, I could do this for any arbitrary jth element. So that's kind of a simple mathematical way to think of it, because you're zeroing out a bunch of terms and only singling out a particular matrix element in that giant sort of matrix or row there. So it's a little strange at first, but once you do it a few times, the procedure will kind of make sense. Because remember, the definition of impedance is essentially a voltage divided by a current. So I'm just saying the voltage excited at the ith port divided by the current at the jth port, or vice versa, it gives me this Z sub ij. Now, there's one extra little notion we want to talk about in this microwave circuit theory, is the notion of a reciprocal network. So more often than not, this is not a universal thing, but any sort of passive circuit with a bunch of, say, capacitors and inductors and without loss will be reciprocal. And in fact, even some lossy circuits may potentially be reciprocal. So don't think of this as a general principle, but it's a special instance that is interesting because it happens a lot in microwave theory. This is a situation where Z sub ij is equal to Z sub ji. So in other words, this matrix Z here is equal to its transpose. So this is a special case that does happen a lot in practice, and so we want to give it a name. And a matrix with this property is called symmetric. Okay, and again, this is not a universal thing that happens all the time, but usually you need something like an active device, like an amplifier or some weird, anisotropic materials to make this happen, or to make it not happen. Okay, but this is not a universal thing. There are special cases where it is not satisfied, but the book does make a big deal that this happens often enough that you can kind of more often than not assume it, except for when those special instances where it doesn't necessarily apply. But this is a very common situation that we care about, and we're going to learn some interesting things about reciprocal networks as we go forward. So, for example, a simple thing like a T-junction of B and C will be a reciprocal network because the impedance between these two ports will not matter which one is being excited. Okay, so that's one way to kind of think of it. If I have a voltage here giving rise to a current here, then a voltage here will give me another current here, and it will occupy the same impedance value here, or will satisfy that same impedance. Okay, so just bear that in mind. We're going to talk a lot about this notion as we go forward. Okay, so that is essentially how you measure and calculate the impedance matrix, and there are many instances where those impedance and admittance matrices will be reciprocal. So just fun fact, by the way, if Z is a symmetric matrix, then so is Y. Okay, so in other words, if a matrix is symmetric, its inverse will also be symmetric. So both of these conditions will be satisfied.